This is the second of our modules on polytomous regression. In the previous module, we have looked at polytomous regression mainly through the use of case studies, examples, and R. In this module, we shall look more closely at the various models. As you know, polytomous regression arises when the outcome is not binary, but rather comprised of several categories. For example, we may choose to categorize smokers as those who have never smoked, those who are currently heavy smokers, those who are currently non-smokers, and so on. A standard practice is to dichotomize the outcome and to use logistic regression, and this is often done for simplicity of interpretation. However, we can of course get more precise and more informative results when we use full-blown polytomous regression. We shall look at several different options, both for the case where we have nominal outcomes and for the case where we have ordinal outcomes, see the details of the fitting procedure as well as some examples to give you an illustration. Learning objectives for this module. We shall first look at the baseline category models for the case where we have a nominal polytomous response. We shall next move to ordinal responses and look at some of the approaches for this kind of data, namely the cumulative logit for ordinal responses, the proportional odds model, and the adjacent category logit model. Logit models for multinomial responses. In this module, we are looking at more details at the situation where our outcome is a categorical variable. You have seen that in the case where we wish to generalize an odds ratio, for the case where we have a binary predictor to a categorical predictor, leads to the calculation of multiple odds ratios for the same variable. Similarly, when we have a polytomous outcome, we will get not one model equation but a series of equations and thus a series of coefficients. Thus, at a glance, polytomous regression is rather complicated, and a simple ad hoc procedure which is often used is to dichotomize the responses so that we have artificially a binary outcome and to use logistic regression. However, we gain more precision and more information if instead we are able to conduct a full-blown analysis. So first, let us consider the case where we have a nominal response. So Y is a categorical nominal response with J categories. We shall first look at the baseline category logit model. X is a corresponding P vector of covariates. Let pi jx equal to the probability of y equal to j given x, and with the restriction that summation over j pi jx is equal to 1. We thus treat the counts as the j categories of y as a multinomial variable with probabilities pi 1x, pi 2x up to pi capital Jx. Logit models will pair each response category with a baseline category. So, in R, this would be chosen alphabetically, but we can choose to denote a particularly relevant choice of the category as the baseline. Often in other software, this is the last one or the most common one. The baseline category logit is then given by pi of little jx by pi capital Jx is alpha j plus beta j prime x for j equal to 1 to capital J minus 1. Note that we have assumed that the last category, which is capital J, is our baseline category. The J-1 equations determine parameters for logits with other pairings of the response categories. This is because for any A and B, we can write log of pi AX by log of pi BX as the difference log of pi AX by pi JX minus log of pi BX by pi JX. Let us look at an example, which is the alligator food choice example taken from the book by Regression. For more details of this example, you are referred to the book by Regression and the chapter on logit models for multinomial responses. So this is a study of factors influencing primary food choice of alligators and is derived from measurements on 219 alligators from the 4 Florida lakes. The nominal response is primary food type and has 5 categories: fish, invertebrate, reptile, bird, and other. So we can fit a baseline category logit model on this data set. Our covariates are G equal to gender, L equal to lake of capture, and S equal to size. We have considered in the previous model the software required to fit the baseline category logit model to nominal data. So if we do this on this data and look at the goodness of fit statistics, we see that the data are quite sparse to begin with 219 observations scattered among 80 cells. The G-square statistic suggests that we can simplify the table by collapsing it over gender. We can also show that adding an interaction term including G does not improve the fit significantly. The G-square and the chi-square values indicate that both the covariates L and S have significant effects. We can also look at a tabulation of the fitted values for various models to get a better understanding of the data. Fish is the most common food choice, and we can estimate the effects of lake and size on the odds that alligators select other primary food types instead of fish. To do this, we use fish as the baseline category, and using the ML estimates of the effect parameters, our prediction equation for log odds is of the form log of pi j hat by pi f hat denoting fish, equal to minus 1.55 plus 1.46y minus 1.66 zb plus 0.94 zo plus 1.12 zy. Y here denotes the size, and zb, zo, zy are corresponding dummy variables. On this slide, we can see the estimated parameters in the logit model for alligator food choices based on dummy variables for the first size and for each of the lakes excepting Lake George. The multinomial logit models can be directly modeled in terms of the response probabilities, and the equation is given by pi j of x equal to exponential alpha j plus beta j prime x by 1 plus summation I equal to 1 to j minus 1 exponential alpha I plus beta I prime x. Here alpha of capital J is equal to 0 and beta of capital J is equal to 0. This is necessary for identifiability reasons. We next come to fitting of the baseline category logit model. This can be done using maximum likelihood. So, maximum likelihood fitting of multinomial logit models will maximize the likelihood subject to the J equations, J minus 1 equations specifying the model. So, for I equal to 1 to n, let yi equal to y1 to yj, yi1 to yi2, yi capital J represent the multinomial trial for subject I. Here yij is equal to 1 if the response I is in category J and yij is equal to 0 otherwise. Then summation over j yij is equal to 1. Let xi equal to xi1 to xip denote the corresponding explanatory variables, and let beta equal to beta1 to beta jp denote the parameters for the jth logic. Now, using the fact that pi of capital J is 1 minus pi 1 plus pi 2 plus pi of capital J minus 1, and yi of capital J is 1 minus yi1 plus yi2 plus yij minus 1, the contribution to the log likelihood by subject I is given on this slide as log of product j equal to 1 to capital J pi j xj to the power yij, which can be rewritten as summation small j equal to 1 to j minus 1 yj log of pi j xi plus 1 minus summation j equal to 1 to j minus 1 yij log of 1 minus summation j equal to 1 to j minus 1 pi j xj, which simplifies to summation j equal to 1 to j minus 1 yij log of pi j xi by 1 minus summation j equal to 1 to j minus 1 pi j xi plus log of 1 minus summation j equal to 1 to j minus 1 pi j xi. Assuming n independent observations and substituting alpha j plus beta j prime xj for the logit in the first term and pi of capital J xi equal to 1 over 1 plus summation I equal to 1 to j minus 1 exponential alpha j prime plus beta j prime xj. In the second term, the log likelihood simplifies to summation j equal to 1 to j minus 1 alpha j summation I equal to 1 to n yij plus summation k equal to 1 to p beta jk into summation I equal to 1 to n xik yij minus summation I equal to 1 to n log of 1 plus summation j equal to 1 to j minus 1 exponential alpha j plus beta j prime xi. The sufficient statistic for beta jk is summation over k xik yi for j equal to 1 to capital J minus 1 and k equal to 1 to p. The sufficient statistic for alpha j is summation over I yij, that is the total number of outcomes in category J. The log likelihood is concave and thus Newton-Raphson methods are required for actual fitting. Because this is complicated, there is an alternative fitting approach which is ad hoc but often used in many statistical software packages. This will separately fit the j minus 1 pairings of responses for j equal to 1 alone using only observations in category 1 or category j of the response variable to obtain estimates of alpha 1 and beta j. And in this manner obtain j minus 1 separate fits of the logit model. So for instance, the jth baseline category logit is a logit of conditional probabilities log of pi jx by pi jx plus pi capital Jx by pi capital Jx over pi jx plus pi capital Jx, which is equal to log of pi jx by pi capital Jx. The separate fitting estimates differ from the maximum likelihood estimates for simultaneous fitting. They are less efficient and tend to have larger standard errors. Baseline category logit models can be represented as a multivariate GLM using the link g of mu I equal to xi prime beta. Here mu I equal to expectation yi is the corresponding vector of expectations, and x is a design matrix with rho I corresponding to the covariates on observation I. The link function is given by gj of mu I equal to log of mu ij by 1 minus mu I1 up to mu I capital J minus 1 for small j equal to 1 to capital J minus 1. Let us move next to the case of ordinal responses. A popular model for ordinal responses is the cumulative logit models. Now note that because it is possible to order the categories of y, it is possible to define cumulative probabilities. Probability y less than equal to j given x as sum of the probabilities pi 1x and so on up to pi jx for j equal to 1 to capital J. The cumulative logit model is then represented by logit of probability y less than equal to j given x is equal to log of probability y less than equal to j given x by 1 minus probability y less than equal to j given x. So the log odds of y being less than equal to category j. In terms of the pi i's, this is written as log of pi 1x up to pi jx with the denominator as pi j plus 1x up to pi capital J of x. Now noting that we can recover the individual pi i's as the differences of the corresponding cumulative logits, it is possible, though not simple, to get the maximum likelihood estimator as before. A particularly simple model for ordinal responses is the proportional odds model. The proportional odds model is specified by logit of probability y less than equal to j given x is equal to alpha j plus beta prime x. So note that beta no longer has a suffix j. This means that we can get logit of probability y less than equal to j given x1 for a value x1 of the covariates x minus logit of probability y less than equal to j given x2 as the ratio of the corresponding log odds, and this turns out to be beta prime into x1 minus x2. That is, it depends only on the differences x1 minus x2. This is possible because the model has the same effect beta for each of the logits. Agresti has presented an application of cumulative odds regression to mental impairment data. So mental impairment data contains a study of mental health for a random sample of adults from Florida and relates mental impairment, which is classified as well, mild, moderate and impaired, an ordinal response in terms of categories which are a life event index, socioeconomic status, and so on. For more details of the application, you are referred to the book by Agreste. He fits a sequence of gradually more complicated models to the data, beginning with the simple cumulative logit model, logit of probability y less than equal to j given x equal to alpha j plus beta 1 x1 plus beta 2 x2, and adding in interactions such as x1 x2. He gives an account of interpretation of the parameters and also comments on the fit of the model. Alternative cumulative link models can be used. These are given by G inverse of probability y less than equal to j given x equal to alpha j plus beta prime x. So instead of using the logit link, we could choose to use alternative link functions, capital G, and it is possible to show that just as we had the binary choice motivation in the case of logistic regression, it is similarly possible to get an equivalent motivation in terms of multiple latent variables in the case where we have categories. So, for example, if we were to assume an extreme value distribution for the underlying latent variables, this leads to the complementary log-log link given by the equation log of minus log 1 minus probability y less than equal to j given x equal to alpha j plus beta prime x. Finally, another model which has been used in many special cases, this is the adjacent categories logit, given by logit of probability y equal to j, given that y is equal to j or j minus 1. So, the logit that y is in the jth category, given that we know that y is either in the jth or the j plus 1th category. So, here again we can construct the various log odds ratios, log of pi j over log pi capital J as the sums in this case. Another model which has received popularity in the literature is the continuation ratio logits, and this is based on something called the continuation ratio, which is log of pi j divided by pi j plus 1 up to pi capital J. In this module, we have taken a detailed look at polytomous regression. Polytomous regression arises when the outcome is a categorical variable. We have first looked at the case of nominal categories and the baseline logit model. We have seen that fitting of this model can be accomplished in two ways. One, a full-blown maximum likelihood, and second, a rather ad hoc pairwise approach which is often used in the software. We have next moved to ordinal responses and seen that there are a variety of approaches possible. Because an approach can be based on cumulative links when we have ordinal data, note that it makes sense to accumulate the probabilities and to look at the probability of y lying in category J or below only in the case when we have an ordinal response. We have looked at several different approaches such as the cumulative regression, proportional odds regression, adjacent categories regression, and regression based on the continuation ratio.